Hello, everybody. Welcome to CryptoCoinMindSet. I'm Keith, and as always, I'm here to help you get your mindset on crypto. You're about to watch one of the guest speakers from the Free State Bitcoin Digital Asset Conference, which was held in New Hampshire on September 1st, 2024. Now, I just want to preface this video by saying I went ill-prepared to this conference. First time I had ever been to this conference, but I went ill-prepared. I should have had a separate Wi-Fi connection. So the video itself is not too great, but the audio works fine. So I hope you enjoy this video from one of the guest speakers at the Free State Bitcoin Digital Asset Conference.
She said, my name's Chris. I've been living here in New Hampshire, I don't know, probably about 10 years now. I live right down the road, only like a minute or two down the road here from Bruce. So there's a couple of us here in Durham, 3 or 4. So just going to talk about a project that I've been working on for maybe over a year, a couple of years now. Kind of started as a bit of a hobby project, and it's kind of transformed into more of it. As was mentioned, I was, one of the couple people involved in creating Bitcoin Cash back in the day. We were kind of very involved in the block size wars. This new project I'm working on is a new cryptocurrency that I'm calling Ilium. And so, it's 2024. There's thousands of cryptocurrencies out there. Why in the world do we need another one? What are you going to bring to the table that hasn't been done? But my history, I guess, kind of with cryptocurrency, I go all the way back to maybe like 2011, 2012 is when I got into Bitcoin. And we knew that Bitcoin had shortcomings, I guess you could say, that, we spent a lot of time and energy back in the day trying to kind of resolve them. And people have created a large number of different cryptocurrencies over the years that have addressed some of these shortcomings in one way or the other. But there really hasn't been one that's kind of solved all of it, right? Still kind of, there's like this nut that hasn't been cracked, where it's just like all the things just in one package. So extensibility being one, Satoshi put this scripting language in Bitcoin to kind of do sort of like these primitive, I wouldn't even call it a smart contract, but some level of scripting. Which was kind of crazy, because if I had designed Bitcoin back in those days, I wouldn't have thought to do that. It would just been like straight transfers for me. So it's kind of crazy you put that in there. But there's limitations to what you can do with that script, and that, of course, spawned Ethereum and other platforms like this that offer kind of more robust smart contracts and extensibility in that sense. Privacy, we spent a lot of time working on privacy back in the day with different types of coin joins. Even in Bitcoin Cash, we had some, like, we called it like Cash Shuffle and Cash Fusion, were these really like advanced coin mixers. But at the end of the day, it's hard to get people to use them, and the user experience isn't great. You kind of want stuff sort of built. Ideally, you want it kind of built into the layer 1, the privacy level. Then we have Zcash, right? And I'm a big fan of Zcash. Zcash is sort of like one of the original privacy coins, and one of the first ones to deploy ZK-SNARKs, which we're going to talk about here. But Zcash has its limitations too, right? It's pretty much just basic transfers, right? You can't do anything more advanced in Zcash in a way that's private. And then fast transactions. I still kind of have, and this might be a little bit of I don't know, like a dream that will never happen, but I still kind of have the idea that one day we can go in the store and like buy stuff with cryptocurrency, right? And so there's the problem there is like the confirmations and the security around like unconfirmed transactions and the speed as it relates to that. So like you go into a store and you buy something with Bitcoin, and the transactions in this unconfirmed state where it can be reversed pretty easily. And you can kind of defraud the merchant fairly easily, and then you can simply wait for the confirmations that doesn't work in all use cases. So fast transaction finalization is something that kind of eluded us. I'm a bit of a fan of cryptocurrency called Avalanche, which introduces sort of a new consensus algorithm that does have really fast finalization. So we'll talk a little bit about that too. And then, of course, the scalability problem hasn't really been solved either. And I don't know if I'm going to solve that in Ilium, but there's kind of some steps to at least head in that direction. So what I'm trying to do is make a cryptocurrency that kind of has all of these things together. It's private, it's fast, it's extensible, it can do smart contracts, potentially scalable, this sort of stuff, Turing complete. So with that, I kind of want to give a little bit of a primer on ZK-SNARKs. So you guys have heard this term before. It's something that I think it's a weird term. It stands for zero knowledge. It's a type of programmatic cryptographic proof. And I think a lot of people hear this term, you're kind of like your eyes glaze over and like, I'm never going to understand this. So I'm going to try and kind of explain this a little bit. And what the point I kind of want to make here is that ZK-SNARKs are these really powerful cryptographic tools, and they've been out since what, like 2015 now. They've been deployed and Zcash came out, but they haven't really been usable in a way that we can really build some cool stuff with. It's super, super difficult to use ZK-SNARKs up to this point. And it's really only been in like maybe the last year that the state of the technology has advanced to the point where now it's kind of usable to do some really cool things with. So when I talk about like it's 2024, I'm working on a new cryptocurrency, it's really because the technology has really only just now become available to start doing this sort of stuff. Even last year you wouldn't have been able to do this. So I have a lot of slides here that would be useful, but no projectors. So I'm going to whiteboard some of this stuff. So ZK-SNARK. Hopefully I can explain it. I like to think that I'm good at explaining technical concepts somewhat simply, but I don't know. This one might be a little too technical for some people. But in computer programming, we have we have a function, right? That can take in some inputs. Okay, and then we have a body of code here, right? This is going to do something. It can read the input, it can mutate it in some way, it can do some computation with it, and then we're going to return an output. Okay, so this input could be more than one piece of data. It doesn't have to be just one. We can have multiple inputs. And the output can kind of be whatever we want it to be. It could be a number, it could be true or false. It's kind of up for us to decide how we want to do this. And all programming languages have this ability to create functions in this way. So what a ZK-SNARK does at its core is it allows us to write a function, a custom function that can do whatever we want it to do, that can take in some input, one or more inputs, and return an output. And what we can do is we can prove, a prover can prove to a verifier that we know some input or combination of inputs that will produce a particular output, but without revealing that input to the verifier. Okay, we're going to give them a proof that says, hey, there's this function here that does something. I know some input that's going to make the function return a certain output, usually true or false. In this case, I might know an input that makes the output return true, but I'm not going to tell you what the input is. I'm just going to give you a bunch of, it's like a proof, which is just a long string of bytes. Yeah. So I'm just going to give you a proof that's going to tell you that this returns true without telling you what those inputs are. Some of the inputs could be public inputs, meaning I do disclose them to the verifier, but then you're going to have private inputs which you don't disclose to the verifier. So that's the whole gist of ZK-SNARKs, okay? Now, in a perfect world, we might have we might have a very thin interface that looks something like this. I'm going to create my function. I'm going to write it out in code. I'm going to pass it into some compiler. It's going to spit out a proving key and a verifying key. And then the prover will just use that proving key, the private parameters and the public parameters, and that will spit out a proof. And then the verifier will just call a verify function that takes the verifying key, the public parameters, and proof. And that will just spit out true or false, okay? Whether it's valid or invalid. So in a perfect world, from a programmer perspective, someone like me, this is how easy it ideally should be to use ZK-SNARKs, right? Just a couple functions. I just define my function, compile it, get the keys, pass it into the proof function, get my proof, verify. ZK-SNARKs are nothing like that in practice. It is insanely hard. So in particular, like when you're writing your code, you're writing code not in like, everyone's kind of familiar with what like computer code at least sort of looks like. You're writing it more in like mathematical equations. So you're writing something like, you're writing stuff like this, and this is how you have to write your code when you're defining that function in ZK-SNARKs. From a programmer perspective, this is like virtually impossible to have to reason about and write code this way. It's super difficult. So anyone who's kind of done anything with ZK-SNARKs up to this point has been doing this sort of stuff, right? So the stuff they've been doing, like with Zcash, for example, go ahead there.
So you're saying that you need to make all these functions and everything, like every time you don't, it's not just automatic.
Oh no, so there are compilers that people have created that can compile down into all these constraints. So each one of these would be an example of a constraint in underline, and a complex program like something like Zcash might have like 100,000 constraints.
So
I'm trying to write a program with 100,000 of these.
Are they the same for every?
No, every constraint's going to be a little bit different.
Like you do different.
Yeah, different proof, different constraint.
Okay, that's like that.
Yeah. So people have created compilers that can compile into this stuff and make it a little bit easier. But there's still some problems. Because this is underlying math, you don't have the tools you would normally have in like regular programming. So for one, in regular programming, we have loops. So you might have a for loop or something, and you can break out of that loop at any time. So like I can have a loop where sometimes it executes 10 times, and other times it executes 1,000 times based on the conditions. When you're writing it in this math like this, there's no breaking out of a loop. Every constraint needs to be executed. So
is this what's sometimes called like the logical circuit? So basically, you have to write out every single possible path.
Exactly. Yeah. So these functions, we tend to call them circuits too. I might use that term later on too. But so we can't break out of a loop. So if we have a loop where maybe one time we needed to execute 10 times and the other time we need to execute it 1,000 times, we have to hit that 1,000 times every time. Okay, we have to figure out what is the maximum number of times through a loop that we need to go, and then we have to do that every time. Also with if and else statements. In normal programming, you have an if statement. If the condition's met, only the if statement executes, and then with an else statement, that wouldn't execute, or vice versa. Only one side of the if and else block executes. But with a ZK-SNARK, you have to execute both, right? And then you can think of the challenge of writing a series of equations where both equations are executed on both sides, but you get the result you want. It's very difficult to kind of reason about that.
So they're polynomials. What are the coefficients? Are they finite field or?
Yeah, they're going to be in a finite field. Yeah.
All right.
So this has kind of been the state of ZK-SNARKs up until very, very recently. Super difficult to use and to kind of reason about and to write these functions from the standpoint of programming. So what this has inspired is people to try to figure out a better way. The way I'm kind of going to describe is, I'm kind of, I worked fairly closely with Protocol Labs. They make IPFS and Filecoin over the years. I know these guys. So there's a guy named Chimed. I can't remember his last name, but he did the ZK-SNARK proofs for Filecoin. And he said it was like, an absolute nightmare to try and do that for Filecoin. And that kind of led him to think about, how can we do this differently? And so he ended up internally inside Protocol Labs creating a side project called Lurk, which is going to be a sort of what we end up calling like a ZKVM or a virtual machine. We'll talk about that term in a second. And there are others. Lurk is the one that I use in Ilium that I have the most familiarity with, but there are other ones like Polygon teams working on like a ZKVM, and there are others. But the basic gist here, or the insight that they have with Lurk is what we're going to do is, in computer science, we have this concept. There's a Turing machine, which is a hypothetical computer that has a certain instruction set, and it can compute a program that uses that set of instructions. Then you have a universal Turing machine, which can kind of take in a description of any other Turing machine and execute its program. Kind of what we're trying to come up with is a function here, a circuit, that kind of acts like a universal circuit, right? That can execute any other program that we can give it. So we're going to create a function that's kind of going to act like an interpreter, right, in code. So our function, our ZK-SNARK function is going to be an interpreter where we can pass in code and then kind of have it interpreted that way. So the approach that Lurk takes is, it's kind of a throwback. There's this paper from McCarthy here in 1960 over at MIT, recursive functions of symbolic expressions and their computation by machine. You kind of really have to go back. There's a lot of, because of the difficulties of working with these ZK-SNARKs and like the resource constraints and everything, it's interesting in that we kind of throw back to a lot of the same resource constraints and optimization problems that they had back in like the 60s, when dealing with computers that had very little resources. So in this paper here, McCarthy basically defines the Lisp programming language. And what Lisp is that it's a way of kind of stepping through a program where you kind of take an input, you transform it, and then you kind of loop through and you go back up and it tells you how to execute the next state of the program. And that's the approach that Lurk takes. Lurk essentially is a Lisp interpreter inside a ZK-SNARK circuit. So one iteration through the program is going to break the program up into a bunch of chunks. And then the first chunk is going to go through the ZK-SNARK and get a proof as the output. It's also going to describe how to continue the computation. So that proof is then the proof along with the way to continue the computation then becomes the input to the next iteration of the circuit through it. So we can step through a program this way, kind of recursively, using something called like incrementally verifiable computation and merging these proofs together on top of each other. So we get something, we kind of get back to like normal programming. So in Lurk, what we can do is we can write a program and it's literal Lisp. So, which Lisp is a really like funky programming language to write in if you've ever written anything in it, but you can write a program in Lisp and it's kind of sort of normal programming, but it gets you back to like loops work the way you expect them to work. Like you can break out of a loop at any time. You don't have to bear like the maximum computation. If and else statements work the way you think they would work, like only one block is executed and not the other block. And this is sort of the general approach that these ZK-VMs are sort of taking. Lurk is probably a little bit unique in that it's basically a Lisp interpreter. Other ones of these ZK-VMs are writing it to kind of more mirror like the instruction set of like a computer, like CPU instruction set where you have registers and opcodes and this sort of stuff. And then with the idea that you could compile down into that. These are just different approaches. I guess we'll see which one kind of wins out, at the end of the day. But this stuff is really kind of only coming online like within like the last year. And it's really kind of transforming the ability to use these ZK-SNARKs practically for practical applications. So the way that I use it, I'll just give you a very basic overview of kind of how I use all this in Ilium. And this part right here is basically just going to be a description of Zcash. But in Bitcoin, we have transactions that are going to have inputs and outputs. All right. Each input is referencing an output in another transaction, and they would call this the UTXO model. So the input is basically, each input is just a pointer. It essentially gives the ID of the UTXO that you're spending. On the output, it's basically not quite exactly this, but you can think of it as the payment address where we're sending the coins to, and the amount is in each output. Now in Bitcoin, this is in the clear, okay? And because this is in the clear, the inputs, because they reference outputs and other transactions, the inputs are essentially in the clear as well. So you can see which address is essentially paying which other address, how much coins are moving, and this sort of stuff. So what we do in Ilium is these outputs contain only the hash of the data. So the hash of the address, not quite the address, but essentially where the coins are being sent to and the amount of the coins, it's hashed, along with a random number that we call salt. This is just so people can't like brute force it and figure out the data behind the hash. So the actual where the coins are being sent to and how much is, you can think of it as being encrypted in a way that the data behind this is hidden from the network. The same thing with the inputs. Instead of having an ID of pointing directly to a UTXO that we're spending, that data is also hashed as well. Okay, so the private data is hashed there, and there's some randomness in there, so you can't brute force it. So if you're looking at these hashes, you're not going to be able to figure out what UTXO is being referenced. Neither are you going to be able to figure out where the coins are being sent to. Now, you just then say, well, how do you validate a transaction? And basically what we do is that we go back to those ZK-SNARKs. So we talked about how you can have you can create a function that has private inputs and public inputs. We have one function just to validate all our transactions. That function has private inputs and public inputs. The public inputs are the hashes. Okay, we just pull them out of the transaction, use them as public inputs when verifying the transaction. The prover, the person creating the transaction, he passes in all the pre-image data behind these hashes. And the function is basically going to verify that it's all correct. It's going to verify that the UTXO exists in the UTXO set. It's going to verify that the output amount doesn't exceed the input amount. It's going to verify that the person was authorized to spend the coins, that he provided a valid signature, this sort of stuff. And the result is we're going to get a proof, and then that proof gets attached to the transaction that gets sent off to the network, and then we can just verify the proof. And as long as the proof verifies, then the transaction should be valid, and it does so without revealing any of this information. Okay.
How many bytes is the proof on general? Like for a small transaction, what's the proof?
It's like 3.5 kilobytes or something like that. It's big, but yeah. I'm a little hesitant to say that because they're changing the back end of workout, and so the proof size is going to change. But I guess we'll see. Yeah. But so this is a basic description, sort of Zcash and how Zcash works. Zcash is only getting us basic transfers, though, where we can just transfer coins from one address to another. But it doesn't allow for anything like smart contracts or any sort of extensibility or stuff like this. The interesting thing with Lurk, though, is in Lurk, they have this concept called a functional commitment, where we can write a function, just kind of like we saw before. We have a function that we can write, and we can kind of take the hash of that function. And then later on, we can, in the course of verifying a program inside the circuit, we can basically verify that that function hashes to a particular hash, and we can check it out. So if that kind of sounds a little bit familiar in the Bitcoin context, that's actually very similar to what is called paid script hash. So in Bitcoin, you have you can write a script in the Bitcoin script. You can take the hash of it. That hash becomes part of your payment address, and that's where you have the coin sent to. So in Ilium, we're basically doing the same thing. And this is kind of the power of the the ZK-SNARKs and LURK and these ZK VMs, in that you write your, instead of writing it in like the Bitcoin script, your script, we're going to write it in LURK, or which is again a dialect of Lisp. And you write your program that, or your little script that way, you hash it, that hash then becomes essentially your payment address. So all addresses in Ilium are basically pay to script hash addresses. And the script gets executed inside the ZK-SNARK circuit. And so when you look at these transactions on chain, you're not able to tell if this is just a basic transfer, is this a more exotic script or anything like that. Everything looks the same on chain because that script is executing inside the circuit. And it's basically validating all of that inside the circuit. And then we kind of go a little bit farther. I go a little bit farther, take some of the things that we worked on in Bitcoin Cash. We worked on something called the transaction introspection, which was sort of enabling the script to read parts of the body of the transaction. And so what I do in Ilium is I pass in all the private and public data of the transaction into these scripts that are executing, so the scripts can inspect the body of the transaction and then make decisions to either lock or remain locked or unlock and allow the funds to be spent based on that. This allows you to enforce what are called covenants. So like I can restrict a script to say like you can't spend this address can only be spent from if the coins go into a specific address, right? And there are other types of covenant, way you can do covenants like that too. That then kind of unlocks something that I call like a recursive script, where you enforce a covenant where each spend from the script requires the funds to go back into the same script. Okay, so every spend from the script becomes like an iteration of a loop, right? So you have like a script that's deployed in the UTXO, and you can only send funds from it if it goes back into the exact same script. So every spend becomes an iteration of a loop, which is basically what a smart contract is on like the Ethereum network or something like this, right? So you have a contract that the function can be as complex as you want it. You can have methods associated with that can be called, and you can deploy it on a network, and then every iteration, every spend from it just sort of sets up for the next spend. And you have basically all the pieces of a smart contract. The UTXOs have a state field attached to it that is also hidden behind this hash. So when you look at the hash, it's the payment address, the amount, the state, and then a couple other things. And so the scripts can read the input state, mutate it, require the new state to be saved in the next iteration of the contract. So you have kind of all the pieces of a smart contract, but in a UTXO context, and in a way that is not revealing any of this information to the network. So when you look at a transaction on the network, you can't tell, is this a smart contract? Is this a basic transfer? Is this some kind of exotic script? The transactions all just look like a blob of encrypted data on the network, which is pretty cool. And like up to this point, we haven't really had that. Like there's some other teams working on projects where maybe the execution of the smart contract is done in zero knowledge, but then the transfers between contracts are not, and you can still see that. This is everything stuff. So even have in Ilium, we have behind this hash on the output, there is a asset ID. So like the UTXO could represent like the native Ilium asset token, but then you could have it represent any other token as well. And so UTXO could represent something else on there. And again, you wouldn't know what an asset is actually being transacted because it's all. All right, so that is kind of an overview, I would say, of I hope I wasn't like super
I understood it.
Yeah.
All right, I hope you enjoyed that video. And if you want to see all the videos from the Digital Asset Conference, check out this playlist right here. In this playlist, I'll have all the videos from all the speakers from the Free State Bitcoin Digital Asset Conference in New Hampshire. So click on this playlist and I will see you there.